Hello, my name is Matthew Taylor. I work for a company called Doulos. We do technical training in various areas, including verification, which of course is relevant for today. I've worked for Doulos for about 10 years. And before that, I worked for Sony, where I did chips for digital TV and mobile phones. So our talk this afternoon is about UVM and formal verification. Is it easy to get started with UVM, or should I use formal instead? So I'm going to start giving a brief introduction to UVM. Only a taster, really, to be honest, because UVM is a big, complicated thing to learn. If you were to buy a training course from us, it would be a 4-day full-time course, and I've only got part of an hour's presentation. So I'm going to give you a brief introduction to UVM, a taster, and then I'm going to move on to formal verification. And I'll do the same thing. I will give a brief introduction to formal verification. Again, it's a training course that I think is 3 days this time, so I can only give you a taster. But when we start talking about formal, I'll also be comparing it with UVM, because that is the subject of our talk, is to compare UVM or formal. Should I be using UVM or should I use formal instead? So starting first with UVM, what is UVM? UVM is the universal verification methodology for SystemVerilog. It is a way of using SystemVerilog for doing verification. And it's a whole bunch of classes, hundreds of classes, and a way of using those classes to do verification. Now, you don't need to know about all of those classes. You probably need to know about a few dozen to be able to use UVM effectively. But it's a big, complicated subject. UVM, it says here, it supports constrained random coverage-driven verification. That is how it is really intended to be used, but you don't have to use it that way. You can do directed tests as well. I did have a customer a year or two ago who wasn't interested in constrained random at all and only wanted to use UVM for directed tests. But it's really designed around the idea of constrained random verification. It's open source. It's also an accelerator and an IEEE standard. So its IEEE standard was standardized in 2017, and there's been a small update since then. And it's supported by all the major EDA vendors. What do we mean by supported? Because it's just SystemVerilog, so any SystemVerilog simulator ought to be able to compile it, but each of the EDA vendors supplies a pre-compiled version of UVM with their simulator, which will also have some customizations for doing things like waveform display and some other things as well. So why would you use UVM? Really, for the same reasons as you might use any kind of methodology. It saves you reinventing the wheel. So you use it for consistency and uniformity, to avoid any mistakes, any pitfalls that you might come across if you tried to invent your own methodology using SystemVerilog. And the other key area, really, the key benefit is reuse. So because it is a standard, because lots of people are using it, then you can buy verification IP, or you can get hold of verification IP that is compatible with UVM from external sources or from other people in your company, previous projects, and so on. You can reuse verification IP environments, tests, and so on from other projects and groups in your company. You can find people who know UVM. You can hire them. You can find know-how, of course. You can buy training courses on UVM from us, for example. So if we have a look at what we might call the big picture, here is a diagram, a simple diagram of a UVM test environment. So we've got the design under test, the DUT at the bottom, and then we've got various components, various blocks in our test bench. And UVM is, as I've just said, a whole bunch of classes. And so all of these blocks would be UVM classes, which usually you would extend to customize them to do whatever it is you want them to do. But some of them actually you use as is. You don't even extend them. They are pre-done, if you like. So if we look at the diagram, you can see that there are 3 blocks called UVM agent. Inside the UVM agent, there are 3 components: a UVM sequencer, a driver, and a monitor. The sequencer generates stimulus, generates transactions. The driver converts those transactions to the ones and zeros that the DUT understands, and the monitor does the opposite. So the monitor interprets the ones and zeros that the DUT is outputting and outputs transactions that represent what the monitor has observed. And that might be for checking or coverage collection and so on. And you can see that those 3 components I've just been talking about are wrapped up in this other layer of hierarchy called a UVM agent. Why is that? Well, because it's useful. It's useful for reuse. So you might have a UVM agent for a particular physical interface, like an AXI interface or I2C or SPI or whatever it is that your DUT is using. Other blocks on this diagram, you can see at the top right there's a block called factory. We're going to talk about that very briefly shortly. The factory is concerned with creating objects or constructing, as we say in object-oriented design. There's also a block called config database. That is concerned with configuring different settings in your verification environment. So you might have different things that need to be set in different ways for a particular project, for a particular DUT, or things that need to be set in different ways for a particular test. A test being a simulation run, a test being what is different between one simulation run and another simulation run. I'll ignore the subscriber and the virtual sequencer because we don't have masses of time, and move finally, or the last thing I'll talk about on this slide is the UVM test at the top. As I've just said, that is what distinguishes different simulation runs. And what you actually are likely to have is many, many tests and one or a smaller number of environments. I missed out the UVM env class. The UVM env class is a layer of hierarchy. So the top layer of the hardware of your test bench, if you like, is going to be all inside a UVM env, and then that is instantiated in each one of your many UVM tests, and each simulation run would use a different UVM test.
So that last slide was effectively space, if you like. Another key part of UVM is time dimension. Sounds very esoteric, doesn't it? But SystemVerilog has phases. Something's happened to the focus. Would you mind clicking on the big thing? Thank you. So it has phases, and phases control the order in which things happen. So the way that you actually make something happen in a phase is in a particular SystemVerilog class, you override a method with the right name. So,
sorry,
isn't it?
I can't hear it on.
Okay.
Hang on.
So I'll keep talking and let you fiddle with it. Okay. You override a method with the right name. So, for example, if you want something to happen in the build phase, as it's called, you override a method called build phase. Now, I'll go through the rest of this code in a later slide, but here's your, if you've not met UVM at all ever, there's your first taste of UVM. Blimey, it's complicated, isn't it? You know, what on earth is going on here if you've not seen UVM? So the point of showing you the code at this point is just to show you how you make something happen in the build phase. And what happens in the build phase is that the different components are created, constructed, as we say. I've still lost focus, I'm afraid. Thank you. So the build phase is where the components are constructed. The next phase is called the connect phase, which you can see is where they're connected up. So code is executed there that connects them, whatever that means. Let's not worry about it at this point. They're connected together. Then there's a couple of phases where, you know, we can, the end of elaboration phase, we can finish putting the test bench together, start of simulation phase, get ready for running the test, and then most important phases on this diagram are the blue ones, and the other sort of essential important phase is called the run phase. And as you saw from that groovy animation just there, that's where the test actually happens. That's where time is actually consumed. These sequences of, you know, this list of phases here is, you know, I'm not going to go through those, but you know, just showing you that, you know, UVM is complicated. One of the first people I talked to UVM to came up with a little advertising slogan for UVM. UVM, it's always more complicated than you think, which it is. And then there's 4 more phases, which you can do other things. But the key point about phases is that they control the order in which things happen. So if you want to guarantee that one thing happens before another thing, put them in 2 different phases. And the other key point from the point of view of this taster session is, you know, UVM is a kit of parts. It's test bench Lego for making your verification environment, your test bench. Here's another example. So I drew your attention to the factory a couple of slides ago. So what in UVM, you don't construct, generally, you don't construct objects directly. You rarely call the constructor yourself. What you do is you call another method, and a class called the factory creates your object for you. And the reason for that is it allows you to intercept that process. And so you write code to make objects of one particular type, and then you write another line of code, perhaps in your test. So this is somewhere low down in your test bench, probably. Number 2 is high up in your test. And you say, for this particular test, please don't create my ordinary transaction. Please create my special transaction instead. Or please don't create my ordinary driver, please create my special driver instead. Perhaps my special driver puts errors in or something like that. And so then when you call the method low down in the test bench that says, please make a my ordinary driver, the factory makes my special driver instead. So, you know, this is very much a taster. This is the kind of thing that UVM is bringing to the party. It's test bench Lego, as I say. So that's the first bit done, and we've lost focus again. Please, could you focus again? Thank you. Could you click on the next slide, the other one, please? That one, and you'll have to click on the big slide. That's it. Thank you. So the next thing I'm going to show you is a very small example of UVM. And the diagram comes in a few slides' time. So I'm going to click through, apologies to you people online, very quickly, and just show you this. This is the diagram of what we're going to create. So it's a very, very simple test bench. We're going to have a sequencer, and there's something called a sequence, which I'll explain in a minute. These generate transactions. They're connected to a driver. The driver translates that abstract thing called a transaction to the ones and zeros that the DUT understands. We're going to instantiate both of those components in a component called an env, which is like a container of components, and then we're going to create a test, which is the controller for the whole thing. So I'll click back 3 or 4 slides, and we've lost focus again. So the first thing we need, what's happened now? I think I may have done that by pushing the wrong button on my remote control. I pushed S, I think, by mistake. I'm sorry.
It's closed it.
Yeah. Apologies, everyone in the room and people listening online. We are good at technology. I shouldn't say that. We are good at technology. Here we go. We're going again. Thank you. This is the wrong presentation because you're showing me hidden slides now. No, this is what's happened. That's not the right. Well, what you were showing me hidden. Those, you see all those slides are hidden. So go down, please. Stop up about 3 slides there.
Cool.
Thank you. It's still not showing on the main screen though. Now it is. Brilliant. Perfect. We're in the right place. So apologies. So the first thing we need is a transaction. I explained what a transaction was when I did my talk this morning, but very quickly, if you don't know what a transaction is, it's an abstract representation of a thing that your design under test can do. So a memory write, a memory read, a CPU instruction, something like that. And in UVM, if you want to create a transaction, and this is a basic transaction that could be some kind of bus access or perhaps a memory access or something like that, you extend a class called UVM sequence item, and you can see that there are 3 data members up here where you could represent some kind of read or write. That's perhaps what command is doing. And then we've got an address and a data here, and you can see that they're a randomizable. Those of you that here this morning, you saw that in basic SystemVerilog. There's our constructor. I'll just ignore that because that's just SystemVerilog. And then here, down here is, this is a UVM taster. It's showing you the fact that UVM uses a lot of macros. So this thing, this is the quote that you use for tick define and tick include and so on. So behind this sequence of 5 macros is dozens of lines of code, and what they're doing various jobs. It's doing stuff to do with the factory, so creating objects of this class, and it's also automatically generating what I call utility methods. So a copy method to copy one transaction to another, a compare method to compare 2 transactions, a print method, and 3 or 4 or 5 other methods as well, all written for you automatically. And if you did our what we call our UVM adopter course at Doulos, that's a 4-day course, and just to give you an impression of how complicated UVM is, we would go into the pros and cons of using those macros. So here is another class. This is called a sequence, and very loosely, a sequence is a bunch of transactions, but very importantly, it's not a passive thing like a list or an array. It's an active thing. It's a container of code that generates transactions. So it's illustrating, again, we're extending some class from the UVM source code called UVM sequence. It's demonstrating that this is parameterized. That's very common in UVM. Here's another one of those macros, constructor. And then to make your sequence do something, you override a task, a method called body, and that, in this particular example, is creating 8 random transactions. And this macro UVM do, yet another macro, is a quick and dirty way of generating a transaction and sending it to, or part of the process of sending it to the driver as well. So confusingly in UVM, we have these things called sequences, which actually generate the random transactions. And then there's something else called a sequencer. And it's one of the things, if you were to learn UVM, that you have to get your head round, you know, what that certainly confused me when I first learned UVM. And what is the sequencer doing then? Well, the sequencer is handling the communication, well, does two jobs, one of which is handling the communication between the sequence, which generates the random transactions, and the driver. And you know, a sequencer is an interesting class because it's one of some classes in UVM that you just use straight off. So the sequence we've extended, and you would always extend the sequence. It would be useless not to do so. Same with the sequence item. We extended that to make our transaction. But the sequencer, we don't have to extend at all. We just have to parameterize it for the particular transaction we want it to generate. So we're back to this again, but I thought it was more valuable to show you this first. So the next thing I think we're going to look at is the driver. Would you mind just turning the monitor round slightly as well? Sorry, I'm being very picky, aren't I? Thank you. So the next thing we're going to look at is the driver. So if you want to make a driver in UVM, you extend a class called UVM driver. It's testbench Lego, isn't it? And here, you know, similar to the code you saw very briefly this morning, if you were here this morning, we've got this thing again called a virtual interface. Don't have time to explain that, but it's a pointer to the DUT, as you can see, as it says there. And then we override a task called the run phase. And you saw that slide about 6 or 7 slides ago, where we overrode the build phase to make things happen in the build phase. You saw the slide with the phases. The run phase is where the test actually runs, where time is consumed, things happen, transactions are generated, the DUT does stuff. And you can see we're going around forever here. And part of the test bench Lego is a standard way that the components talk to each other. And this line of code here is getting a transaction from the sequence. So the sequence item port is something that you get for free with this UVM driver class, and that's to do with how the components talk to each other. So again, we've only got an hour. It's a 4-day course just for UVM. Trust me, that's how we get the sequence from the sequencer. So we now have this class. REQ is a variable that is of class myTransaction, which is the transaction you saw 3 or 4 slides ago. If you remember, it had data members called command, address, and data. And so these 3 lines of code are copying the information from inside this abstract thing called a class via the virtual interface to the corresponding pins on the design under test. So there is an example of our a test bench component. So we're using classes for the data, if you like, the transactions, and for the structure of the test bench. So here's the next level up. You've seen this code before. This is what you saw about 10 slides ago. So we're now extending a class called UVM-env, which is like a dumb layer of hierarchy in some ways. That doesn't have to be that dumb, to be honest. Here's our macro again. And then here is our sequencer and our driver. So the way that you instantiate components inside other components in UVM is they become data members of what we call the parent class. So these are child classes of this parent class. Usual sort of constructor has to be done. We will ignore that. Here is the build phase. So this is the code I drew your attention to briefly before. So these 2 lines of code are being executed in the build phase. And looks quite scary. What on earth does that mean? Basically, there is a class called type ID, which is declared inside the driver class. You might just click back a slide. You might say, well, I don't see that. Where is that? Well, oops. I was looking for some macros, but there isn't some macros there. Never mind, you'll have to trust me. It would say tick UVM component utils, and there's dozens of lines of code behind that macro, one of which is this type ID class. And so what we're doing is we're calling a static method called create on this class, which is declared by that macro, which actually wasn't on the slide, unfortunately. And the reason for doing that is, as I said before, rather than calling the constructor directly, we call this other method called create because it allows us to intersect that process. And if we have written a line of code, perhaps in our test, to tell the factory to create something else, this line of code could create a special sequencer or a special driver, which you might need for a particular test. So there's another example of the kind of facility, if you like, that UVM's offering you. And then here in the connect phase is where you connect stuff up, as the name suggests. We are connecting our driver to our sequencer. So, I can't go into the details of how that works, but hopefully it's pretty obvious that, trust me, that we are connecting one thing to another thing, and one of those things is called the driver, the other thing is called the sequencer. So finally, we need the top layer of our whole environment, and that is the test in UVM. And so to create a test, you extend the UVM test class. And in the test, you would instantiate your env. Now, in a real environment, you've probably got envs inside envs or envs inside envs inside envs. But in this simple environment, we've just got one layer of hierarchy. And in a real project, you would have one or a small number of envs and then lots of tests. So you've got the same env and you're going to instantiate it again and again and again in zillions of tests. And the test is, as I say, what distinguishes two different simulation runs. And so you would override the run phase again in your test and write the code that makes your particular simulation do whatever it is that particular simulation is supposed to do. So, what you're basically going to be doing, or a good part of that code is running the sequence. So we saw that class called the sequence about 5 slides ago, which had the loop in it that created 8 random transactions. Well, this code here is creating a sequence. So it's creating an object of class mySequence via this sort of roundabout method. It's then randomizing it. I'll come back to these 2 lines of code in a minute, and then it's calling a start method on that sequence, and that start method calls that body task that you saw a few slides ago, and then so that's what kicks off the whole simulation run, basically. So to come back to these 2 lines of code here, it's just an illustration of yet another facility that UVM offers you. So one of the things that needs to be thought about is managing the end of your test. How do you know when the test should stop? The chips that I've worked on have been radio receivers, and we used to run them for an integer number of something called a superframe plus 5 symbols. Why plus 5 symbols? Well, because the data path was 4 point something symbols latency, and so 5 symbols flushed out an integer number of these things called superframes. That's really easy to get your head round. If you're doing a radio receiver, garbage in at one end, garbage out the other end, easy peasy. What if you've got a much more complicated design under test? These CPUs that people have been talking about in the big lecture theatre with, the guy from Brecker with all these, caches and branch prediction, and when are you going to work out when to stop that test? Much, much harder to do. And so objections is a mechanism that's built into UVM that makes that job easier, basically. So, just very quickly, what it does is it allows different parts of the test bench to object to the test finishing. So a stimulus generator could say, well, the test shouldn't finish yet because I haven't generated all my stimulus. Possibly a checker could say, well, the test shouldn't finish yet because I've got some expected outputs, but no corresponding actual outputs. So don't finish yet. That kind of idea. So there's much more to it. You know, as I've said, you know, our UVM adopter course is 4 days long. So you know, we've had 26 minutes. So we can't go into any more detail, but you know, there's many other things to talk about. We haven't talked about checking at all. We haven't talked about coverage at all. But the next thing we need to talk about is formal. That simulation. So talk in general terms about simulation this morning. Formal is a completely different idea. So what I'm going to do now is introduce you to the concept of formal and refer to simulation as we, you know, now and then as we go along, and then we'll finish up by comparing the two. So, you know, what is formal? Formal is mathematically proving that your design is correct. So you might mathematically prove that what your design is the same as another design, or you might mathematically prove that your design doesn't violate a set of rules. And you can use it for all sorts of reasons. So one of the key ones is finding bugs. If you get a design that you think is correct and try formal out on it, it will almost certainly find a bug in your design, even though you've taped it out and it's in, you know, 10 million mobile phones or whatever, you still will probably find a bug very quickly in it. So bug hunting in general, assurance, what are we talking about here? We're talking about, you know, proof that the design, you know, proof that there are no bugs, rather than just generally finding bugs that we didn't know were there. If you see the subtle difference between that. A nice thing about formal tools is they can write their own rules. Sounds a bit incestuous, but they can. And so they can check the, well, one of the EDA companies calls this part of their formal tool Superlint. And you know, I'm not saying that EDA tool is any better than any other EDA tool, but I do like the name because it describes as a training person exactly what's going on. Superlint, yes, it's like lint, but better. And so it can do things like array bounds checks and say, well, if this happens, that array will go out of bounds, and that kind of thing, which ordinary lint can't do. Connectivity, can this part of your design talk to that part of the design? Coverage waivers, you know, they were talking about coverage holes in the big lecture theatre earlier this afternoon. You're going to simulate to the heat death of the universe if it's physically impossible for that coverage hole ever to be filled. And so formal technology could tell you, well, that value will never happen. That coverage bin will never ever get hit. It's impossible. And so you can just say, well, that's green then, to use the terminology that the AMD guys were saying. Key thing, you know, using formal, especially if you have to write the rules yourself, it really does force you to understand the spec, really does expose the spec, any ambiguities in the spec. That was also talked about in the big lecture theatre. You know, specs are written in English or French or whatever. You know, they are ambiguous and woolly and incomplete and so on. And then, I mean, you can use, this is no way an exhaustive list. Post-silicon debug, right? You get your chip back, doesn't work because this thing happens. So how do you use formal to find that? Well, you write a rule to say this thing should never happen, run it into the formal tool, and the formal tool will say, yeah, it can, because look, if I do this and that and the other, look, it happens. And so it can help you with your debugging there. So formal's not hard to use, actually. It's really quick to get going. You know, you can write, well, you can do, you know, half a dozen GUI clicks, or you can write some kind of tickle script with half a dozen lines of code. You give it your RTL code, you know, read in the code, possibly compile it, something like that. You say, this is the clock, this is the reset, go and check it. Thank you. And off it goes. So you give it your RTL code, you write some properties, and let's have a look at some examples of those. So here is a very simple block of RTL. You can see here's the actual, I mean, we've got the design and the properties in the same module. That's not completely unrealistic, but it may not be the case. So we've got this simple block of RTL here that you can see that on the rising edge of the clock, if cell A is high, Q goes to QA, but if cell B is also high, Q goes to QB. And then we've got two properties here written in SystemVerilog SVA, which are checking, these are specifying how this design should work. So they are saying that if cell A is true, then on the next clock cycle, Q should equal the previous value of QA. And if cell B is true, then on the next clock cycle, Q should equal the previous value of QB. And if you're astute, you'll know that there's something wrong here. It's not a mistake on my part. That's intended. So there are two properties. And so we've got our design that already existed. We've now written two properties to check the design. And so we push the go button. When you're playing with it, you click on the play symbol or whatever it is. Really, it would be a command in a tickle script. And it goes away, and one of three things can happen. Ideally, this is the one you want. It proves that the rules are correct. Well, the design is correct, relative to the rules. That's not going to happen in our case, if you noticed that already. What would happen in our case is that one of the rules would be correct and the other rule would be falsified. And so what the tool will do is you'll give you what's called a counterexample. It'll say, aha, but if cell B and cell A are both high, then QA doesn't necessarily equal the past version. Sorry, Q doesn't equal the past version of QA. And then the third outcome that you could get is what's called an inconclusive proof. And this is where, formal experts, people who are using formal earn their money, because what will often happen is that the tool will run for a long time, and you probably would set a timeout limit and it'll come back and said, well, I don't know, haven't managed to prove it yet, sorry. And then, obviously dealing with that is, a large part of the art of running formal. So here's an example of like a command line output that you might see from a tool. So here we said we've got two assertions. You saw those in the code just before. And here we're saying that two of them were covered. So I haven't got time to teach you SVA, but it said if this, if the left-hand side was true, check the right-hand side. This covered is saying, yeah, the left-hand side happened. So you do want the left-hand sides to happen. There are three outcomes with formal, well, and with any kind of assertion, even if you're simulating it. There's pass, there's fail, but there's also, well, the left-hand side, the conditions of the left-hand side, the if part of it never happened. Therefore, I never checked the right-hand side. Therefore, well, that's called a vacuous pass, and so that's basic. I mean, it's not a fail, but if the condition on the left-hand side, it's called the precondition, on the left-hand side was never true, then you haven't tested your design properly, basically. So both assertions were covered, and then one passed. So that's good, and the other one failed. CX is counterexample. So in the event of a counterexample, what tools will do, and they all do this. So I mean, obviously the EDA vendors will be able to tell you the differences between their different tools and why theirs is better than their competitors. But they all have this basic functionality, and so what they will all do is put some kind of time, well, there's various ways that they can display it, but here is one of them, like a waveform like this, showing you the conditions in which your assertions fail. So apologies to those online. I'm going to click back a few clicks to go back to where we were, so we can look at the assertions. If you hadn't spotted it already, it's this first one is going to fail, because if cell B and cell A are both true, then Q is going to equal QB, not QA, isn't it? So that is the failure mode, the counterexample that the tool has found. So if we go forward again and look at this waveform, if you look at it carefully, you can see that cell A is high, cell B is high, and Q, that's this one here, is not equal to QA. So our property has failed. It's proven it to be false. And obviously we set this example up deliberately. Another sort of, caveat, if you like, obviously it's, trivial in example, but it needs to be trivial so that you can evaluate it quickly in a training situation. In a real project, it's not going to be so obvious. So you've got these three outcomes, three possible outcomes. Proof, great, fantastic. Counterexample, well, not so good, but you found a bug, basically. And of course, that bug might be in your property. It might be in your what's called your formal test bench. It isn't necessarily in the design, but that's the same with any kind of verification. And then you've got this third outcome of like an inconclusive proof, and that's where time is going to get consumed. And what I mean by time, I mean is your time. Project, are going to start moving rightwards, to use the phrase. So in the case of the inconclusive proof, you need to decide what to do next. And one thing you could do is listen to one of our webinars or take one of our training courses and learn about all the different things that you can do to basically narrow the problem down so that the tool has a chance of proving this assertion that won't be proved. So moving, going down another layer, little bit about what's happening behind the scenes. Your design is going to have a zillion flip-flops in, and each flip-flop can, well, let's restrict it to 1 and 0s, can be 1 or 0, and so the number of possible combinations is 2 to the power of the number of flip-flops in your design, which is, it's not fair to call it astronomical, because the number of atoms in the observable universe is just irrelevant compared with the number of possible combinations that there are in even a normal, a small design. And then you've also got a time dimension as well. So you've got a zillion flip-flops, 2 to the power of a zillion, to the power of the number of clock cycles. We're exploring this absolutely enormous, what is called a state space. Obviously, your tool can't remember all of those states. That's not how it works. It works by manipulating Boolean equations. So here's a diagram of a state space. So there's like one possible, assuming that all the flip-flops are reset, there's one reset combination point in the state space. And then as time progresses, very quickly, the number of possible states that your design can be in is just going to be absolutely enormous. And here's where we start comparing formal with simulation. So here is what simulators do. Simulators explore a single path through the state space. You might call this a golden thread. And so if you've got another simulation, it might be a different path through the state space. And the third simulation is another path through the state space. And as I've just said, we might call those golden threads. And so part of the art of verification of simulation is choosing the set of tests, the set of threads that explore the important parts of that state space, because you're going to, the fraction that you can actually explore is, like a Planck length in the, or an infinite number of universe. It's just, tiny fraction of it. But what formal is doing is exploring the whole state space, literally the whole state space. Or what it's trying to do is to explore literally the whole state space. As I said, it does that by manipulating Boolean equations. It doesn't literally have every possible combination of 1s and 0s in its memory. It couldn't possibly do that. And so that's what it means here by state spaces represented symbolically, represented as equations. And if you're writing an assertion, that defines what is called a target state. And reaching the target state with an assertion is a bad thing. And so what the tool is trying to do is show that you can reach that target state. And if it can reach that target state, then disproven the assertion. There is also another thing, and we'll see it in a minute, called a cover. So rather than an assertion where you're saying this should always happen, this should always be true, a cover is where you say this should be possible. So it should be possible that the full you've got a FIFO design under test, the full output should go high. That should be possible. That would be a useful thing to try to prove. So if you're trying to prove a cover, you're trying to prove that you can get to the target state. So here we've got a rule, very absurdly simple. You wouldn't, well, I guess it's absurdly, it doesn't matter. We've got a rule, and we're saying if there's a request on one clock cycle, then on the next clock cycle there should be a grant. And so the target state that we're trying to find is the situation where there's a request on one clock cycle and there isn't a grant on the next clock cycle. And if we can reach that state, then our rule has been disproved. If we can't reach it, well, then that's good. That's what we're aiming for. So either way, what we have done is we've explored a proportion of the state space. And sometimes this is called a golden nugget. And obviously you'll have more than one rule. And so what you're trying to do is explore the whole state space, and each of your properties is exploring part of the state space. And part of the art of formal verification is is knowing that you have got enough rules in order to explore the entire state space. And there are various metrics that your tool can calculate. So one is called cone of influence, for example. Another one is called proof core or formal core that allow you to judge that. So, yes, it sounds nice. My tool can mathematically prove that my design is correct. But when the rubber hits the road in the real world, skill and experience and knowledge is required in order to actually do that with a real design and assess whether you've done it thoroughly enough. There's no good at proving that your design meets a set of rules if the rules are too woolly or inconsistent or have holes in them and so on. So your tools will help you judge that. So why did our rules fail? A little bit about that. Here's another view that one of the tools would give you, and you can see that, as we saw in the graph, in the waveforms just now, that if cell A is true, and in this example, Q is 0, so that where these red arrows are pointing for those online, QA is 1, then you can see that Q is not equal to $pasq. And so, we know why that is, because it's a trivial example in a training scenario. But nevertheless, what can we do about it? Well, what we presumably, let's assume that there isn't a bug in our design. So the problem isn't that there's a bug in the design. The problem is that we've given formal too much freedom, and it's tested an illegal state. So, assuming that there's no bug in our design here, it seems reasonable that cell A and cell B shouldn't both be high at the same time. And so what we want to do, or one thing that if that's what we want to do, is to remove that possibility from the state space, basically from the possibilities that the formal tool tries. And so what we would do, or one way of doing it, is to write what is called an assumption. So here, can you see, instead of saying assert property, we're saying assume property. And we're saying assume property that cell A and cell B are never both high at the same time. So now we've excluded the illegal combination from the tool's explorations, basically. And so now it would pass, basically. There's also another SVA command called restrict, and the subtle difference between assuming and restricting is you would use assumptions to eliminate illegal conditions, and restrictions are used to eliminate conditions that were causing your proof to take too long, basically. So to restrict even more so that we can actually achieve something. So perhaps we'll just restrict ourselves to being in mode A, because trying to test all 14 modes at one go is too much, that kind of idea. And then just by way of illustration, what we've got here is a cover property. That's the fourth thing that you can do with a property, where, as I've talked about, 10 minutes ago or whatever, this combination of inputs, so it's both cell A and cell B being low, we're saying, prove that that is possible. I mean, of course it is, because these are variables that the tool is driving itself. But as I keep saying, it's a trivial example. A real project, these things are not going to be obvious. That's why you're using the formal tool. So we are nearly there. What do we do when things go wrong? What are the, just dive into a bit more detail about what can go wrong. So you can have false negatives due to assertion bugs. That's effectively what we had. We didn't really have a bug. There was nothing wrong with our rules. The false negative was because we didn't exclude an illegal combination of inputs. And so we got a counterexample. We debugged the counterexample and basically found the problem was in our formal test bench, not in our design. I mean, that's the same as normal, but it's simulation, isn't it? It's quite possible that the bug is caused by your test bench being wrong rather than your design being wrong. I guess actually, no, I've just sold that to you wrong. Really, I guess the situation we had actually was the second one. Apologies. There was nothing wrong with our assertions. I was being too general. The problem was under constrained inputs. So when you write assumptions, what you're doing is constraining the inputs. You can't just do any old nonsense. You can only do this more constrained set of sensible things. And so apologies, what our problem was this second one here. So we got a false negative because we were testing an illegal state, basically. You can also get false positives due to over-constrained inputs. So a wrong assumption. We know about assumptions in life. Making wrong assumptions is always a bad thing. Well, it's a bad thing in formal as well. As you might imagine, this is a trickier one to deal with, just like it is in life. How can you deal with that? Well, there's various ways that you can learn about to deal with that. And covers are one of the ways of dealing with that. So what you do is you write your assumptions to say this should be, don't test this, don't test that, don't test the other. And you then write some covers to say, make sure this is possible, make sure that's possible. And it could be the case that if you've made a wrong assumption, that means one of your covers is now not possible because you wrongly excluded it from the mix. Another thing you could do is simulate. So here's where formal and simulation are getting back together. When you simulate and assume, it turns into an assert. So if you assume that this thing can't happen, and then you execute your assumptions with your test bench, and your test bench generates that supposedly illegal combination of inputs, you might think, they're not illegal after all, are they? Because the test bench generated them. So you've got that another way of feeding back and checking that you haven't made a wrong assumption. And that's really the key difference between assuming and restricting. Restricting is because you're just restricting it to break the problem down. You're not excluding illegal conditions. Simulators ignore the restrict statement, but they turn the assume statement into an assert so that they can check the assumptions. So that's another way of checking your assumptions. This is highly likely to happen, false positive due to not having enough assertions. What can you do about that? Well, touched on that already when we saw the diagram with the yellow golden nuggets. There are various metrics that your formal tool will be able to report to allow you to assess how much of your design, how much of your state space you have explored. And then the last one is the hardest one, overly permissive, wrong, if you like, assertions. That's your skill and judgment as an engineer. perhaps review them, or something like that. So we are nearly there, as I said. Perhaps we're not quite as close as I thought. Well, no, we are. So how do you actually use formal? Well, one thing you might, probably better to use it from the get-go. I've already said that if you apply formal to a design that already you think is okay, almost certainly will find a bug. Bit like lint. If you've used lint, you have to use lint right from the start. Otherwise, you'll just get a zillion errors, and it'll be impossible to manage. So good to be doing it from the start. As I've said, it forces you to think about the spec, particularly if you're writing properties. It really does force you to think carefully and identify deficiencies in your spec. As I've showed you, you can put the properties in with the RTL itself. And the nice thing about that is that when you reuse the RTL, you reuse the properties, but necessarily the best place to put them. Another place to put them is somewhere else. And that gives you what you might call a formal test bench. Something that we haven't talked about yet, you probably heard, if you know anything about formal at all, formal is best for control logic. That's a sort of generalization. It is easier to check control logic than data path. And the simple reason for that is that the state space is smaller. And the simple reason for that is because control signals tend to be 1 bit wide. They often are anyway. Data path almost certainly isn't 1 bit wide. So if you've got a 16-bit data path, the state space is just 65,000 times bigger than if you've got a single bit control signal. But you've also, you can write assertions for like white box, low level, local things. If there's a request, there should be a grant within 10 clock cycles. Or you can do more global things. If I put this data in the input to my chip, then that data should come out at the output of my chip. That's a different kettle of fish. That's likely to be a much harder thing to prove, and is going to take a lot more work and skill and experience on the part of the engineer. But ultimately, you are trying to prove that your chip does the thing what it's supposed to do, not that it always went from this state in this state machine to that state in the state machine. You're trying to prove that it actually demodulates digital TV or whatever it is that your chip is supposed to be doing. So, end-to-end assertions could be valuable, but comparing with simulation, that now may be where your simulator is earning its keep, rather than writing rules and trying to prove it. But there are various techniques that you can use to enable yourself to to allow yourself to be able to check the whole design. If I put this data in, does it come out in the right way, type stuff. So formal and simulation have, as it says here, different strengths and weaknesses. Basically, you saw the graph, the golden threads. That's simulation. It's a narrow, deep exploration of the state space, where formal is a probably shallow, but certainly wide exploration of the state space. So it's completely thorough, but testing your whole design over 1 million clock cycles, going to be hard, basically. Not impossible necessarily, but hard. Probably 1 million might be pushing it. So they complement each other. So, I mean, if I might missold you the lecture, should we use this or this? Well, no, you should use both of them, actually, because they do complement each other. They have their strengths and weaknesses. And part of the art of verification is thinking in a different way to the designer. And formal forces you to think in a different way again. So that's a positive thing. So final slide, should we be using UVM or formal? As I've just said, yes, we should use both of those. Of course, we should be doing simulation. Formal, certainly not yet, cannot replace simulation. It's it's adding more stuff. So simulation is giving this narrow but deep end-to-end, does my design really demodulate digital TV? Formal is a wide but shallow exploration. that was, I think, no, I'm not sure what happened there. I probably accidentally pushed ESC again when my trouble is it's the next button. You just push the slideshow. That's at the top, that one there.
Oh, there we are.
Yeah. There we go. And I've got to go, that's all right, I'll do it. Try not to push ESC. Apologies, people online, look away. There should be some kind of warning for epilepsy for this, but you'll have to put up with it. Right, flashing images, that's what they say, isn't it? We're nearly there. Final slide. So formal, it complements simulation. It's a wide but probably shallow exploration of the state space. So it's a different idea. You should be using both. So as I introduced myself at the beginning, I work for a company called Doulos. We are a training company. Our business is training engineers. We have lots of courses in the stuff I've been talking about. UVM, we've got a UVM adopter, advanced UVM. We've got 2 formal courses. So essential formal is the introduction to formal. And we also have a new advanced formal course as well. Various HDL, SystemVerilog, VHDL, Verilog, and so on, and all sorts of other things that you can see on the slide here. Thank you. Any questions?
Yeah.
Yes.
So when you worked out with under constraints that check cell A, why did you add the assumption rather than modifying the constraint to say when cell A is high but cell B is not?
Okay, sorry, let me go back to the slide and then it didn't all get, that's good enough. So you're saying what we added an assumption saying they should not both be high at the same time. So what are you saying we could have done instead?
Why do that rather than modify the check cell A property to say when cell A is high but cell B isn't?
Okay, that's a very good question. So basically in this first property, we'd say when cell A and not cell B then. I mean, we could have done, I think it's going back to my excuse that this is absurdly trivial, but in a real project that might not be so obvious. So your properties are likely to be much more complicated, and I mean what you've said could be doable, but you'll find you have to edit all of your properties to say, oh, and also not this, whereas you could just say in one place, assume this is never the case, if you see what I mean.
There's also, if I can.
Yeah, no, please do. Yeah, I know you're an expert.
So another reason is that usually you want to have assumptions for things which are relevant to all properties.
Yeah.
Right. So you don't actually have to write the same assumption at all as precondition of all properties. It's an environment constraint, so it's going to be valid for all. So you can have it separate.
Yeah, if you go forward a few slides to the that one, sorry.
Oh, yeah. This one. No.
The false positive, false negatives. Sorry.
That one.
That one, yeah.
Right. Okay.
Yeah, so obviously that last one is, as you say, the challenge. I was wondering, are there any tools yet that can handle that? Because that is a real big problem. Like if you've written the assertion wrong, then you potentially do have a bug. And you also have this mindset that you don't have a bug because you've got an assertion which you think checks it. So I've been in a team where there was an assertion which was wrong and therefore it was a bug, but actually it's, you've got an issue with your assertion and you can't really trigger it because there's no way of creating that case to trigger that your assertion is wrong.
I mean, I don't know a tool. I don't know the man from Cadence sitting in the corner here. I don't know whether you can say a particular tool.
So usually as was said about coverage, right? So for false positives, usually coverage is one way to go. You can write manual covers, but usually our tool, for example, will have coverage added to all of the design. So if there are unreachable items in the design, and we can mathematically prove that they are unreachable, can be a tip to false positives. And false negatives, it is just like an iterative loop that someone writing a formal test case will have to go through. Now, I guess when you talk about the quality of proper sheets, it's a hard thing because you as a human, you are translated from a spec into an SVL English, right? So it's very hard to actually tell that you as a human did a good job. One way of doing this is, for example, if you have like people were talking about formal isoformal previously, when you automatically generate properties from a spec which is machine readable. So you remove the human out of the equation, but actually testing what the human's intention is a bit hard. The tool has tips to give you to point you in the right direction, but people will eventually go back to you as an engineer, I think.
I suppose another thing is what I mentioned this morning. You've got, I mean, it's quite woolly, but validation. You know, we're doing verification here. We're trying to check that the design is the same as the rule, but we could also make an FPGA prototype and try it out, perhaps run it in an emulator or whatever.
Yeah. So, but if we could just go back one slide again, I was just wondering. So so if for our checks cell A, we had by mistake said cell A Q equals past Q, we left out the A.
Right. Okay.
But we thought that we were checking cell A. There's no way to, because of that would always pass, there's no way to sort of determine that we've made a mistake with that decision.
That one would, because it would, when you run the what's called cone of influence. So cone of influence is a fairly dumb sort of structural check. Proof core is a much more thorough check. One of those or both of those would say, oh, you're not checking QA. QA is not having any influence here. So in that particular example, part of the tool would find that.
It means that the solver did not have to use the expression to find proven result.
Okay.
So your coverage would.
But if you had done past Q, if you done Q equals past QB, then you wouldn't detect that.
Well, again, you wouldn't be testing QA again, would you? So I mean, I'm not. That's not like a golden answer, but for this particular scenario you raised.
Thank you.
Are there any questions on? Oh, there's another one.
Just a quick one. Just wondering what you think of other simulation tools like CocoaTV.
I've absolutely. Oh, I would say. Sorry, I thought you were going to say. Ask me to compare EDA vendors, and I would never ever do that. CocoaTV, I haven't really used it, so I have no opinion anyway.
Who's your favourite EDA vendor?
Well, I'd have to shoot you. No, I don't. I really don't have a friend. I absolutely do not. Are there any questions online? For you?
Yeah, there's quite a few.
Nobody's got a train to catch. Okay, I have a question. Driver and monitor, what is the best approach to avoid delayed cycles? Should I use non-blocking assignment groups? It's another way to handle that. Not sure I understand. I mean, I understand the individual concepts, but I'm not sure I understand how they're put together in the question. I mean, are you? I mean, perhaps there's. I don't know. I'm going to answer the question, but I'm going to sort of slightly guess what they're asking. So if you're talking about controlling the timing between the test bench and the DUT, I'd use a clocking block. I think possibly that is the answer to the question. I don't know why I'm walking back over there because I can't read them. Any look back? I'm sure what that question means, I'm afraid, if there's any look back about the training. How can formal take part in post-silicon debug? I don't know when that's, but I think I answered that in the thing. You create a people won't be able to hear us online if you talk, guys. Sorry. So you create the bug and prove that it can't happen, and presumably it can happen because that you've seen it in the real silicon, and so the tool will help show you how that bug happens. Where's the best place to put my SVA in the UVM environment? SVA can't go in classes. So I would say in an interface is a really good place. As I know, assertion property or formal verification is static. Yes. How can we make sure that we verify the correct design without running? Understand that one, I'm afraid. How many? Don't understand those two, I'm afraid. I'm sorry. Okay. Ah, right. Oh, I see. Okay, sorry, I'm not understanding. Are there any that haven't been answered? That was the one that's this morning, actually, isn't it? So how can you set? I think we better make this the last one because we're running out of time. So the last one was how can I set a limit for the number of clock cycles, which was also asked this morning. You can say an infinite number of clock cycles, but there are dangers in doing that, whether you're simulating or trying to prove with formal. So it's better not to do that, or it could be better not to do that. So what you should have is a reasonable upper bound. What you could do is run some kind of high level simulation to actually get a realistic upper bound for the maximum time you might have to wait for something to happen. I've got one more question in the room.
For that, can we just put up a condition saying that if so and so happens, then just stop the whole program instead of having a time limit?
It's not a time limit, it's a cycle limit. So if you say, if there's a request, how long would I ever have to wait? What's the maximum time I'd have to wait for a grant? Probably better to have run a high level, system C or something simulation to establish that rather than just guessing or saying wait forever. It's not really a question of how long it takes for the tool to do something. We probably should stop there, shouldn't we? So thank you very much, everybody. Thank you for folks online. Oh, before you go, we've